You ever wonder how scientists actually come up with the big ideas? The theories that really shape our world? It can seem like this, mysterious process, but it's really a craft. And in this explainer, we're going to break it all down and show you the actual tools for building and refining scientific theories.
Okay, so let's just dive right in. If you've ever read an academic paper or been anywhere near that world, you see this word everywhere: theory. Top journals, they're always demanding a contribution to theory. So what's the deal? Why this obsession with something that can feel, so abstract?
Well, here's the problem. This constant demand for new theories, it can totally backfire. It can lead to this flood of ideas that are inconsistent, untested, and, ultimately, they just don't help us understand the world any better. It can actually get in the way of doing good science.
All right, so here's our roadmap for this explainer. We're going to start with the theory problem, then talk about who theory is even for. After that, we'll get into what makes a theory good, then we'll explore how science grows by building and pruning knowledge, get into the nitty-gritty of improving theories, and wrap up with one of the biggest challenges in science today. Let's do it. Okay, first up, the theory problem. And look, this is not just some dusty academic debate. The quality of our theories has real, tangible effects on how we solve actual problems out in the real world. So, what is a theory anyway? If we strip away all the jargon, it's really just our best answer to the question, do we understand what's going on here? That's it. And for our example today, we're going to use employee turnover. A theory of turnover is just trying to explain, why do people leave their jobs?
And a good theory isn't just for researchers locked away in a lab, it's a practical tool. But different people need very different things from it.
So think about it. For a manager who's dealing with high turnover, a theory is only useful if it's, usable, right? A theory that says turnover is caused by someone's personality, what's a manager going to do with that? You can't change that. But a theory that points to a bad compensation system, now that is something they can actually fix. They need stuff they can act on.
Now, for researchers, a theory is kind of like a map. It shows all the territory we've already explored, the stuff we know for sure. But maybe even more importantly, it highlights all the blank spots on that map. It literally tells us where to go next and what big questions are still out there waiting to be answered.
And for students, theories are like mental models. They give you a structured way to look at a complex problem like turnover. It's a framework for diagnosing the root causes and thinking systematically about how you'd even begin to solve it.
And finally, this is a big one that's often overlooked: policymakers. They rely on theories all the time to create effective laws and regulations. A good theory helps them predict if a new policy is actually going to work. Under what conditions and who it's going to help. It guides the very principles of how we're governed. Okay, so we know who uses theories and why they're so important. But the big question is, how do we tell a good theory from a bad one? Let's actually build ourselves a toolkit for evaluating these ideas. And this brings up a really key distinction. See, a brand new theory is only potentially good. It's a fresh idea, it's untested. It doesn't become a good theory until its predictions are actually backed up by cold, hard, real-world data.
All right, here's another crucial distinction you got to know. On one hand, you have a unit theory. Think of this as a super-focused explanation of one single causal link. For example, employees with better skills have more job options, so they're more likely to leave. Simple. But on the other hand, you have programmatic theory. That's the whole shebang, the entire body of settled science, everything we think we know about a topic like turnover.
And I love this analogy for it. Proposing a new unit theory is exactly like trying to join a conversation that's already happening. You can't just jump in and start shouting, right? You have to listen first. You have to understand what's already been said, that's the programmatic theory, so that your new idea actually makes sense and connects to everything else.
Okay, now let's talk about significance. Because when you test a theory, you usually get a result, and that result is often a number. So, for example, take a look at this. The finding that taking an aspirin can reduce your chance of a heart attack by just 0.11%. That sounds tiny, right? Almost nothing.
But this is where context is absolutely everything. Is that tiny number trivial, or is it a lifesaver? Well, think about it. Given how incredibly serious a heart attack is, and how cheap and easy it is to take an aspirin, that tiny little effect suddenly makes a massive difference. So practical significance, it's not just about how big the number is. It's about the cost versus the benefit in the real world.
We tend to think of scientific progress as just adding new ideas to a pile.
But it's not. It's also about cleaning house, about actively testing and getting rid of the theories that just don't hold up. It's a process of both building up and pruning away.
And one of the most powerful ways to do that pruning is something called strong inference. The best way to think about it is like a horse race. You take two competing theories that are trying to explain the exact same thing. Then you design one critical test, one experiment, where they go head-to-head and only one of them can possibly win. It's an incredibly decisive way to figure out which explanation is stronger.
Now there's a big difference between failed confirmation and true falsification. Failed confirmation is just, hey, we tested this theory and it didn't work out. But falsification is so much more rigorous. It's about systematically ruling out all the other plausible explanations until only the strongest one is left standing.
The great philosopher of science Karl Popper gave us this fantastic way to think about it. Imagine truth is something in the middle of a field. A theory is like a big fence we build around where we think the truth is. Now, we can never see the truth perfectly, but every time we falsify a bad idea, we get to shrink that fence, bringing it in a little closer. We're getting closer and closer to reality.
But what happens when a theory is just too vague to even be tested or falsified? Well, it enters this really predictable and totally unproductive cycle. First, there's a ton of enthusiasm. Then people try to apply it, but the results are all over the place, inconsistent. That leads to disappointment and then confusion. And eventually, everyone just loses interest and moves on to the next shiny thing. And we never actually learned anything.
So, what's a better way? Instead of just constantly chasing new theories or tossing out old ones, how do we actually improve what we already have? Well, we do it through a process called theory elaboration.
And theory elaboration is the right move, but only if you can answer yes to 3 key questions. So here's the first one. Is there already an existing theory to build on? And is there data you can actually get your hands on to test it?
Okay, question number 2. Is the current theory's explanation flawed in some way? I mean, is it controversial, or maybe just too ambiguous, or is it just plain inadequate for explaining what's going on?
And third, and this is crucial, can you bring some fresh evidence to the table? Theory elaboration isn't just reanalyzing old stuff. It really requires collecting new data to push the theory forward.
So if you can say yes to all 3 of those, then it is absolutely time for theory elaboration, and there are 3 main ways to go about it.
The first approach is called contrasting. This is all about testing a theory's boundaries to see where it breaks. You can do this horizontally by testing it in a totally new context, like a different country or industry, or you can do it vertically, testing it at a different level, like seeing if a theory about individuals also works for an entire team.
The second approach is construct specification. This means we're refining the actual building blocks of the theory. You might do that by identifying a completely new concept that's been missed. Or, and this is super useful, you can do what's called construct splitting. That's where you take a really broad idea, like turnover, and you break it into more precise parts. For instance, is it functional turnover, where a bad employee leaves, which is good, or is it dysfunctional turnover, where one of your star players quits? Those are 2 very different things.
And finally, there's structuring. This is all about improving our understanding of how the different parts of a theory actually connect to each other. We can define totally new links between ideas, we can map out the precise sequence of events, what causes what, or we can even describe complex feedback loops that unfold over time. All right, for our final section, let's zoom way out and talk about one of the biggest challenges facing, well, pretty much all of science today. And that is the grand challenge of bridging what's known as the micro-macro divide.
And this divide really is like a giant chasm. On one side, you have all the micro theories. These are great at explaining the behavior of individuals, psychology, small groups. But then way over on the other side, you have the macro theories, which explain massive systems, organizations, industries, entire countries. And the problem is, these 2 sets of theories, they almost never talk to each other.
And this matters a lot. It creates this huge gap between science and practice. Because guess what? Real-world problems don't care about our neat little academic departments. They exist at all levels at the same time. This divide just leads to confusion. And you get scientists in different fields basically reinventing the wheel instead of just learning from each other.
So the ultimate goal here, it's kind of like the search for a grand unified theory in physics. What we really need is a grand organizational theory that can elegantly connect the micro to the macro.
one that can explain how millions of individual actions scale up to create huge organizational outcomes, and at the same time, how those big systems shape the way individuals think and act.
And that leaves us with a final, and I think really crucial question. The world isn't just one or the other. It's made of both nuanced individual stories and massive large-scale data. The biggest challenge for all of us, then, is how do we best integrate these two ways of knowing? How do we build a more complete, a more useful, and frankly, a more accurate picture of our world?